This assessment asks us to predict the product of the Wittig reaction on screen. Recall that the Wittig is the reaction between a carbonyl, aldehyde or ketone, and a phosphonium ylide. That phosphonium ylide is named as such because one of the resonance structures that we can draw of the ylide will have a negative charge on carbon and a positive charge on phosphorus. Now, mechanistically, this is like any carbonyl addition reaction in that the strong nucleophile will attack the carbon of the carbonyl, pushing electrons up. The difference here is that this will undergo a rapid ring closure when the alkoxide attacks the phosphonium that came along with it. This oxygen-phosphorus bond is pretty strong. In fact, one of the stronger bonds that we study in organic chemistry. That gets us to here. Now, that oxygen-phosphorus bond is strong, but four-membered rings are not particularly stable. And so this is going to undergo a sort of retro-cycloaddition. We'll understand what that means later on. But where this CO bond is going to break, with those electrons moving there to form a new phosphorus-oxygen double bond, another very strong bond in organic chemistry, and these electrons pulling away from the phosphorus to form an alkene. And so the product of any Wittig reaction is going to be an alkene. In this case, it's here. As we always do, let's number our carbons to make sure we have the product correct. So 5-carbon ring, we'll call this carbon 6, 7, and 8. According to this scheme, we should be forming a bond between 7 and 1. So this is 7, 6, and 8. This was carbon 1, 2, 3, 4, 5. All of our numbering checks out. And so this is the alkene product of the Wittig reaction.